we can have this kind of statement. Delta U would be equal to integral Cv dt. Okay, we discussed about this yesterday, and in addition we also have this condition. When the condition is in constant pressure, the heat capacity would be defined as Cp, because this one is in constant pressure. By definition, it would be dH over dt at constant pressure, so we can have this relation. Delta H would be equal to integral Cp now dt. So now you know the difference between delta U and delta H. Remember, even though it's only a function of temperature, because it's considered as ideal gas. For undergraduate program, most of the calculation would be based on ideal gas, even though you will learn how to evaluate based on real gas. But most of the time, the calculation would be based on ideal gas. Now, let's go into detail regarding with the Cv value. So Cv is in a constant volume. There are this kind of, when I explain about ideal gas, remember that there are two types that normally occur, monoatomic and diatomic, or other type of it. So not including in monoatomic or diatomic. So for monoatomic ideal gas case, an example of this is helium, argon, krypton, and so on. Because it's only one molecule only consists of one atom. And in this case, only translational energy that has an effect. So the value of Cv for this type of ideal gas is 3/2R. Okay. On the second one, the diatomic ideal gas. It's like oxygen, nitrogen, and so on. So double atom. The movement of the molecule is based on translational and also rotational. So because of additional molecular movement, the value of Cv is increasing. That's why in this case Cv is equal to 5/2R. And how about the one that's not included in monoatomic or diatomic? For that case, not only translational and rotational, but for other gas, rotational and vibration will also increase the value of Cv. So most of the time will be higher than 5/2R. Remember, this R is the same R that you normally know in universal ideal gas formula. This is the same R that when you know this formula, PV is equal to nRT. So the same R. You can use 8.314 joule per mole Kelvin or 0.082 liter atmosphere per mole Kelvin. Okay, so this is the value of Cv based on monoatomic or diatomic ideal gas. Now let's move on. Recall this formula. PV is equal to nRT. Since internal energy is not a function of volume and pressure, we can consider this relation. Cp is equal to Cv plus R. Okay, so please remember this relation. Cp is equal to Cv plus R. What would be the effect? Okay, before I go to the system, the effect would be I will come back to this slide first. For monoatomic, Cv is equal to 3/2R. Let's calculate the Cp using the previous formula. Cp is equal to Cv plus R. So for monoatomic gas, what would be the Cp? It means 3/2R plus R, right? And the result would be 5/2R. This one is for monoatomic gas. Let's try to calculate for diatomic. Can you help me? What would be the value? Come on, use the same example as I showed it previously.
Is it 7/2R, sir?
Okay, correct. Good. Yes. So now you understand Cp and Cv value for both monoatomic ideal gas and diatomic ideal gas. Now let's move on to this is, I'm pretty sure you already know about this condition. When you have a closed system, remember, first we will focusing on closed system. In isothermal case, it means delta T is equal to 0, where the final temperature would be equal to initial temperature. If this is the case, let's try to break down everything. Remember the first law of thermodynamics, delta U is equal to Q plus W. Delta U itself is integral Cv Cv delta T. Because delta T is equal to 0, delta U would be equal to 0. In this case, Q would be equal to minus W. This one you should put a minus sign because it's in opposite direction. Okay. So remember with this one. You can calculate based on this, or you will have any other information that normally you will use, because PV is equal to nRT and the temperature remain constant. It means P1 V1 would be equal to P2 V2. This is the standard formula that you normally use for isothermal calculation. Okay, I'm pretty sure you already aware about this. Now let's move on to isochoric or isometric first. Let's skip isobaric at the moment. In isochoric case, it means delta V is the one that equal to 0. What would be the effect? The effect would be to W or work. Remember, for closed system, again I emphasize on closed system, is equal to integral P dV, integration of P dV. Since delta V is equal to 0, this value would be equal to 0. In other words, we will have the result of the calculation would be work equal to 0. Again, let's use this formula. Delta U is equal to Q plus W. Since W is equal to 0, W would be equal to Q. That's why you can find this formula, because it's coming from Q is equal to delta U. And remember, by definition, delta U is this one, CV delta T. Okay, now let's move on into isobaric. In isobaric case, delta P is the one that equal to 0, same pressure. So isothermal, same temperature, isochoric or isometric is the same volume. Now in isobaric, it means same pressure. The initial and final pressure remain the same. So if it is the case, the formula for first law of thermodynamic will still apply. Delta U equal to Q plus W. Now, the Q itself, since it is isobaric, in the constant pressure, we should use Cp because it's in constant pressure. This is the key. How about W? W will remain the same. This is the formula for W. So this is the same. This is the formula for W. But remember, you need to calculate also delta U. What is the formula for delta U in isobaric case? You don't need to change anything. Delta U is always like that. Delta U is equal to integral CV delta T, even though it is in isobaric condition. The one that changing is only the heat capacity in heat. Okay, so now you can calculate for each case, isothermal, isobaric, and isometric, the value for each unit in first law of thermodynamics. I will repeat. For example, isothermal, when delta T is equal to 0, this will lead to delta U equal to 0. Because delta U equal to 0, we can have this relation. W is equal to minus Q. And then you can use this correlation. In isobaric, you can use the similar correlation. So it means V1 over T1 is equal to V2 by T2. That one is isobaric correlation. Similarly, for isochoric or isometric, you can use P1 by T1 is equal to P2 over T2. Okay. So just remember from the initial one, you can use this relation P1 V1 by T1 equal to P2 V2 by T2. When you have an isothermal condition, just remove this value. Oops, sorry. Remove this one. When you have isobaric, so the relation would be P1 V1 is equal to P2 V2. When you have isobaric condition, just remove this one. So the relation would be V1 T1, V1 over T1 is equal to V2 by T2. And the last one, when you have isometric condition. Let's use another color. Let's use this one. So V1 and V2, it will remain the same. So you will have this kind of relation. P1 by T1 equal to P2 by T2. Okay, any question up to this point before we go into adiabatic condition? Any question? No? simple, right? So at least you know the basic principle from your first year in this university. So now we will go more detail. Let's evaluate the adiabatic condition. So in adiabatic case, there will be no heat transfer from the system to the environment. So if we write delta U is equal to Q plus W, this value is equal to 0. In other words, delta U would be equal to work. So if you want to calculate work, just use by definition delta U definition. Remember, delta U is equal to CV CV delta T, while delta H is always CP delta T. So never change this formula. But for heat or work, it will be depend on the thermodynamic process, whether it's isobaric, isothermal, isometric, or adiabatic. But for delta U and delta H, by definition is always like this. Delta U equal to CV delta T, while delta H or enthalpy is equal to CP delta T. Now let's move on to the detail of adiabatic. What is the details of adiabatic? We can remember in your last quiz. Actually, we cannot use this simple P1 V1 over T1 equal to P2 V2 per T2. In adiabatic, this one is not applicable. Why? Because there is additional parameter that incorporated into the system. What kind of parameter? This value, gamma, or some book mention it as K. What is the meaning of gamma itself? So by definition, remember Pasanggono always emphasize when you have three stripes, the one like equal, these three stripes means definition. So the researcher and scientists who understand in details regarding with the thermodynamics, they already give this kind of definition to make the calculation much easier. So gamma or K by definition is CP over CV. So because we know this relation, we can prove this one. In monoatomic case, gamma is equal to 1.67. Where does it come from? Can you guess? Just use this CP over CV. For monoatomic, CP is equal to 5/2R, while CV is equal to 3/2R. Please recall this one, or we can revisit. Okay, this is the value of CP and this is the value of CV. Remember both of these values. Now let's return to this one. It's the same, right? CP is 5/2R and CV is 3/2R. From here, we can predict the value of gamma. gamma is equal to Cp Cv means equal to 5 by 3 or equal to 1.67. You can do the same thing for diatomic. Remember, the Cp for diatomic is 7 by 2R and Cv is equal to 5 by 2R. So you can calculate gamma as 7 by 5. That's why the result is 1.4. Any question up to this point? Okay, if you want to know the details, the relation between this formula in adiabatic condition, you may check from literature, the one more or less like this. P1 V1 gamma is equal to P2 V2 gamma. And if you have the relation between P1 and T1, it would be different. Just make sure each relation between pressure, volume, and temperature, you need to put gamma as one of the parameter. It can be in P, the power in P, the power in volume, or in temperature. It depends on the condition. Okay. Now, you can determine the work based on this formula. Okay. In the end, for closed system, you can have this relation. Work is equal to R T1 divided by gamma minus 1. Remember, gamma is this value. It depends on the type of the gas, whether it is monoatomic, diatomic, or polyatomic. Okay. Times inside the bracket the ratio of the pressure, power gamma minus 1 over gamma, and then minus 1 in the end. Why this formula is very important? Most of the evaluation for compressor and expander, turbine for example, compressor and turbine, we can predict the ideal performance based on this formula. And it's relatively easy because you only need initial inlet temperature. This is the inlet temperature, T1. And then this one is pressure ratio. If you want to compress with a certain compressor, you can find from the specification from the data sheet for compressor that the pressure ratio, let's say 4. What does it mean? When you have P1 as an inlet in 1 atmosphere, at the outlet of that compressor, you can have 4 atmosphere. That is the meaning of pressure ratio. So basically, P outlet divided by P inlet, and use the same gamma. So because of this, the ideal or theoretical work can be calculated directly using this formula. Okay. The next one that I want to emphasize is the other work, but with S as a subscript here. So the previous one is only work, only W. Now WS. This is work shaft. This formula is normally used for open system. The bottom one is for closed system and the upper one is for open system. Try to check in detail. What is the difference between work for open system and work for closed system? The first one is related with gamma and K. In the closed system, most of the book will use this gamma term. But when you have an open system, most of the time they will change into K instead of using gamma. But the meaning remains the same. That one is only to distinguish which one is open system, which one is closed system. But the meaning remains the same. That one is ratio Cp by Cv. Okay. And we can neglect this one if we consider N as 1 mole. So we can eliminate that one. RT1, P2, P1, everything is the same. The only difference is there is additional K in this part that you cannot find here. No gamma in this area. Okay. So, in other words, in ideal case, work in open system is equal to, wait, something like this. Work in open system is equal to gamma times gamma or K times work in closed system. I will change to K instead of gamma. Okay, so this is what normally used as an engineering prediction at the beginning, whether they want to use a closed system or an open system. The device itself will be a different one. Similar compressor, but different principle. Later on, you will understand there will be a difference between centrifugal compressor and positive displacement compressor. So there will be two different types, compressor or pump. The first one is centrifugal. This is based on open system. And the second one is positive displacement. Positive displacement. This is based on closed system. Okay. So this is the unique things about adiabatic. Ideal condition for compressor, pump, turbine will be based on adiabatic condition. Please understand this principle because we will use it again when we discuss second law of thermodynamic. In the second law of thermodynamic, we will evaluate the efficiency of heat engine and heat pump. Heat engine like the one in the Otto cycle in your gasoline car, or based on diesel engine, you can evaluate the performance based on all of these thermodynamic paths. So please remember how isothermal work, how isobaric and isometric works, and also adiabatic works, including all the calculation. Okay? Any question up to this point? If not, I will have two more or three more slides. But before that, in a real situation, the heat capacity is a function of temperature. You remember when I discussed previously that Cp is equal to Cp is equal to 5/2R in the monoatomic case, and for diatomic, Cp is equal to 7/2R. Remember, I already mentioned to you about this. But in a real situation, Cp itself is a function of temperature. Here, it seems that Cp remains constant, even though the temperature is changing. In a real case, Cp is a function of temperature. When you increase the temperature, the value of Cp will change as well. And each component has a different formula. It means the value of B, C, D, this one should be E. E and F, all of this value is different, depend on the component. Later when Pak Sanggoro explain about how to read same table, you will understand about this value as well. Because it's not easy to read that table, and there is additional information that you need to practice. So basically, the weekly quiz is to help you to practice. Once you understand the quiz, that is the minimum requirement for completing this course. So that is what's so called by the objective of the course. As long as you can understand all the weekly quizzes, you will pass the minimum of this course, the minimum objectives of this course. Later on in the exam, we will give you additional question that may be a little bit harder to check whether you can understand even the more complex one. Okay, now please understand this condition. There is a reversible and irreversible case in thermodynamics. The simplest example you can find based on this diagram. Let's say you have a system on the left which consists of a certain gas, and you put an insulation on it. You lock it using this stopcock valve. This is the initial state. When you open this one, you will go the irreversible process. Why? Because once it flows, due to a pressure difference, once you have a P1 and the vacuum in P2, because you already opened this one, it will reach an equilibrium maybe somewhere in between P3. Why this one is irreversible? Because if you lock or if you close this stopcock, the state of this final condition will not be the same as the initial one. Okay, it's not the same. You cannot reverse this condition. Now let's try with another example. Okay, you have a fluid here. And then there is a load using lead shot put on top of it. This container should be isolated using thermal insulation. And then we can heat up this condition using thermal reservoir, increase the temperature. So this is the initial state. What will happen? The heat will be absorbed by the system. The fluid will receive extra energy that coming from the heat. And the gas will start to expand. What will happen? Because of this expansion, there will be an increase in volume. So, because of this thermal insulation, which is the thermal insulation, remember this is similar with Joule experiment. Even though you already turn off the thermal reservoir, it will remain at a certain point. But if you release the thermal insulation and the heat can go out from the system, it will return to the initial value. That's why we can consider this one as reversible process. Now try to connect with the previous explanation. Isothermal, isobaric, isometric, or adiabatic, all of them can be reversible and also irreversible. The most important part is the adiabatic reversible. It will be introduced with the new term when you consider as adiabatic reversible. Okay. Now, this is the adiabatic process that we discussed previously. Remember the one that I told you? Now the relation is different between, we cannot use P1 V1 by T1 equal to P2 V2 by T2. We cannot use this one for adiabatic process. Instead, you have to use this condition. Okay, please be aware of this. So normally I will use this relation T1 V1 gamma minus 1 equal to T2 V2 gamma minus 1, or T1 P1 1 minus gamma over gamma equal to T2 P2 1 minus gamma over gamma. Or the last one is P1 V1 gamma equal to P2 V2 gamma. So we need to use this relation. We cannot use this one. Okay? So please remember about this condition. Now, remember the expansion and compression process that we just discussed. This is how you draw it in a PV diagram. Pasanggono already emphasized on this one as well. I just want to repeat, so hopefully you can understand this one in detail. Okay, so this is the small sigma delta. When it's equal to 0, this one is isobaric process. So this is isobaric. You can see from the same pressure from the initial and the final state. How about isothermal? When this one is equal to 1, there is a curvature, there is a curve, but with a smoother slope. To differentiate, to distinguish which one is isothermal and which one is adiabatic, just make sure adiabatic is always steeper compared with isothermal condition. And for the same volume, this would be the same. And remember what Pasanggono mentioned, in the expansion case, the volume will always increase. It's expand, except for isochoric or isometric process, because the initial volume and the final volume remain the same. So how can we distinguish which one is compression, which one is expansion? In isochoric or isometric case, check this value. The initial value compare with the final value. P2 is lower than P1 for isochoric. That is the condition of expansion. Okay? So in the opposite way, this is compression process. You want to compress something. So the volume will shrink. This is the initial volume, decrease to smaller volume in isobaric process. Again, remember, when you want to compare isothermal and adiabatic condition, be aware of the slope. The adiabatic is always give steeper slope compared with isothermal. And the last one is isometric or isochoric. Again, because this one is in the same volume, we cannot use the term, the definition that the initial and final volume. But you can use the difference in this part. Final pressure and the initial pressure. When you have an increase in pressure for isochoric or isometric process, we consider that one as compression process. Okay? Up to this point, any question? If not, let's go into a bit detail. Remember, by definition, work is equal to integral P dV. And check this diagram. This is PV diagram, pressure to volume diagram. So we can estimate the work based on the area under this curve. Let's check with the simplest one. Let's use this condition. For expansion process, this is the initial one, and this point is the final state. This one is isobaric process. So how can we calculate the work based on this diagram? Remember, this formula, work is equal to integral P dV. It means that the area under the curve would be the work done by isobaric. So this is the initial one. We will have V1 here. Take also this point, we have V2. So the area under the curve is considered as work for isobaric. Okay, any question up to this point? If not, let's compare with the second one. The second one is isothermal process. To make it easier to understand, I will remove this shadowy area. Now the final condition is here for isothermal. I will remove this point as well. The initial still remain V1 and the final remain V2. But now the curve is different, not isobaric curve, but isothermal curve. Now let's draw the area under the curve. So the area would be like this. Okay, so work for isobaric is the highest one. The second one is work for isothermal. You can see from the area under the curve. Now the last one. I will remove this one. The last one is for adiabatic. If you want to compare, it should be apple to apple. So number 2 should be somewhere here. I will extrapolate this curve and reach this point. And what would be the area? Just use the same principle. Just annotate the area under this curve. This one is for adiabatic process. So now we know that this is the work at adiabatic. And how about isochoric? We cannot find the work done by isochoric. Remember that the work for isochoric or isometric is equal to 0. Right? So for sure, that one would be the lowest one. Okay, up to this point, any question? And remember, for expansion, it means the work done by the system. So it's not the work that given to the system, but work done by the system. So the result of the work will always be negative for expansion. So the last one is compression. The same principle, I will not go in details, but for the compression things, it means that we put the work on it. So work result would be positive. The system have additional work. And you can use the same thing to calculate that one. Work is equal to integral P dV. So you can draw the area under the curve. But please be aware, you have to use the same initial and final volume. If this one is V1, this should be V2. So you need to compare apple to apple. So for example, this is 2 for the 2 for isobaric, 2 for isothermic, and 2 for adiabatic. Okay, then you can do the same thing. Put or calculate the area under the curve. Okay, I think all of the information regarding with the basic thermodynamic process I already covered here. We will discuss how to read in a real case. Pak Sanggono will mention how can you read heat capacity as well as steam tables based on your knowledge on each condition: isobaric, isothermic, adiabatic, and isochoric. In fact, later on, we will revisit again the steam table to understand the meaning of isenthalpy and isentropy. But that one is after we move to the second law of thermodynamics. Okay, do you have anything to add, Pak Sanggono, before you discuss about steam table?
No, I think that's sufficient.
Okay, thank you very much, Pak. Any question from you guys? No? Okay, if not, I will give the screen to Pak Sanggono. Please, Pak.
Okay, thank you, Pak Hari. Now, I will upload the material that for the preparation of the test. Okay, can you see table of thermodynamic properties? Please respond.
Yes, sir.
Yeah, okay, yeah, figure 6.5. It has been described by Pak Hardev previously. So this is the y-axis is pressure, but it is in logarithmic scale, and then the x-axis is enthalpy. It is in the linear scale. And then there is a dome over here. Follow the number. We have number 1, number 2, number 3, number 4. Okay, let me make it bigger. Okay, pressure versus enthalpy, we call it Molar diagram. Okay, depending on the substance that we select, in this case, we will use methane, and then later we will use water, H2O. Okay, just to refresh your memory, we have this dome. At the top of the dome, there is a critical pressure we read the critical pressure over here, okay? We put C over here as a critical point. On the left side of the dome, we have liquid. That is the lower part of the enthalpy. In the right-hand side over here of the dome, we have vapor, okay? So, if I ask you, the enthalpy of liquid versus enthalpy of the vapor, which one is higher? It is vapor, okay? The enthalpy of the vapor is higher than the liquid. If I have liquid from point number 1, it is 100% of liquid. Suppose if I have this as water, H2O. Number 1 is liquid water. And then I increase the enthalpy to the right. To the right is to this direction. Okay. What I get on the right hand side of the dome is the water vapor. If it is on the right hand side of the dome, we call it superheated vapor because we do not have any liquid over here. If we have it inside the dome, that is between point 2 and point 3, we call it saturated fluid. What is that fluid? If it is close to the left hand side over here, the majority is liquid because it is any points over here, we have liquid and vapor. But in the left hand side, we have more liquid, less vapor. On the right hand side here, for instance, if I have a container in a piston, that container contains liquid and vapor. If the majority is vapor, then the location is on the right hand side over here. Okay. Since it is inside the dome, we call it saturated vapor over here. On the left hand side, we call it saturated liquid. So in the terms of saturated, it means we have both liquid and vapor. If we have more liquid, we call it saturated liquid. If we have more vapor, we call it saturated vapor. Over here, we call it superheated vapor. Number 1, it is just liquid. We call it subcooled liquid. Okay. Now it is clear. Number 1, 2, 3, 4, and in between. Okay, up to this point, are there any questions?
Excuse me, sir. Can I ask a question?
Yeah, go ahead.
So when I see the chart, I doesn't see any number regarding to like the range of pressure or enthalpy where the material is solid, liquid.
Okay.
Do you have other chart that has the values for the pressure, or it is not relevant? Thank you.
Okay. So if this curve or this Molar diagram is for H2O, water, then we have that liquid, vapor, and mixture of liquid vapor of the water. Okay, and we put that in a steam table. We call it steam because we have vapor, we have liquid, because we don't have solid in the steam table. But from the steam table, is it possible to recognize this point? That means the enthalpy of this point or the pressure of this point. The answer is yes. Okay. So in the steam table, we can recognize this point. We can recognize any points inside the dome. And we can recognize also points on the right hand side over here. That is the superheated vapor. Therefore, we will have superheated steam and we will have saturated steam. Okay, that is the scope of our discussion in the table later. Okay, and there is one more. You will learn this next week, I think, from the second law of thermodynamics, that is entropy, that is S. Entropy is the degree of orderness or disorderness. Later we will go through the unit, but the principle of the entropy is how ordered are the molecules. If we have a comparison, the entropy of liquid is low. The entropy of solid is even lower. The entropy of solid at 0 Kelvin is defined as 0 entropy. Okay, if we have the entropy of vapor here, it is high. So entropy going higher is going higher to the right hand side over here. Okay, this is Molar diagram, and then there is also temperature versus entropy. There is a dome also, and in the dome of the temperature versus entropy, the left hand side, the lower entropy is liquid. The right hand side, the higher entropy, this is entropy, the higher entropy is the vapor. In between, that is inside the dome, we have liquid and vapor. Okay, now I go to another example of methane. It gets complicated, but it is simple. Once you understand this, it will be simple. It has been uploaded in the Microsoft Teams of this course. Okay, if you want to download, you may download. It is Molar diagram of methane. It is not for steam. It is not for water. But the reason I put this curve is so that you understand the meaning of enthalpy, of entropy, temperature, pressure, volume. Okay, so in the Molar diagram, it is pressure versus enthalpy, P versus H. The same thing as what we just discussed. This is P, this is H. This is log of the P. Okay, now let's read over here. This is 0.1, this is 1, this is 10. Okay, if I have 10 over here to the power of 1, I have here 10 to the power of 2. Over here, 10 to the power of 0. Over here, 10 to the power of minus 1. Okay, so that means that is the meaning of the logarithmic. Now try to read. Let me zoom in. Okay. The unit of the pressure is megapascal. So over here, this is 10 megapascal. Is it the log or the pressure? The log of the pressure, natural logarithm of the pressure, or is it the pressure? The answer is this is the pressure. This is 10 megapascal. This is 100 megapascal. In between, we have 20 megapascal here. We have 30 over here. Okay, as a comparison, let me scroll a little bit. This is 1 megapascal. This is 10 megapascal. Over here, this is 2 megapascal. This is 3. This is 4. This is 5. So the point is this. From 1 to 2, it is longer than from 9 to 10. That means that is what the natural logarithm means. Okay. So this is 1 megapascal. Now we have the dome over here, and then we have a curve. It is written as S equal 5. This is S equals 6. What is S? S entropy over here, specific entropy. What is the unit of the entropy? What is entropy? Entropy is energy. If we call it specific, it is per unit of mass or per unit of mole. So specific entropy is energy per unit of mass per unit of temperature, Kelvin over here. Okay, so the unit of the entropy is kilojoule per kilogram Kelvin. What is the unit of the enthalpy? Let's check. The unit of the enthalpy is kilojoule per kilogram. What is that kilogram? Kilogram of methane, because this curve is the curve of methane. Okay, now about the temperature. We have the horizontal line over here. Okay, it is written as T minus 150. The temperature of this line is minus 150 Celsius. How do I know it is Celsius? Because in the box over here, it says the temperature is in Celsius. It is not in Kelvin. Okay. This is what we call isotherm. Okay. This is at temperature minus 150 also. This up to this and then up to this. Now let's check minus 100 Celsius. This is the temperature minus 100 Celsius. It goes to the right hand side over here. Let's follow. We read over here minus 100 Celsius, the same temperature in this line. Okay. And we can follow this to the left hand side. Over here, this is the same temperature, minus 100 Celsius. Okay, up to this point, are there questions? Clear, it is clear enough. This is minus 100 Celsius. We have dome, remember the dome. In the left hand side of the dome, we have subcooled liquid. On the right hand side of the dome, we have superheated vapor of methane. Inside the dome, we have saturated liquid of methane. We have saturated vapor of methane over here. Okay, how about exactly at the middle? Do we call it saturated liquid or we call it saturated vapor? Well, actually it doesn't matter. If you want to call it saturated vapor, it is fine. What if over here, then we call it saturated vapor? Actually, it is fine also. As far as you understand that saturated means we have liquid and vapor. Okay, so in between, if I have a point over here, it is closer to the liquid here. Okay, so the majority is liquid. Maybe 80% liquid, and then the 20% is vapor. What is that percent? That is percentage in mass. So in this point, if I assume I have 100 kilograms of methane, then 80 kilograms is liquid methane, and then 20 kilogram is vapor of methane. What if I have over here? If I have 100 kilogram of mixture, 70 kilogram is vapor of methane, and then the 30 kilogram is liquid. Why is that the liquid is only 30? Because it is far away from the liquid area. Okay, so along the line over here, on the left hand side, I have 100% of liquid. On the right hand side here, I have 100% of vapor. Okay, up to this point, are there any questions? Still simple. Okay, now I want to ask you about the estimate of the temperature, estimated temperature. We have the dome over here. We have the temperature minus 100 Celsius here. Over here, the line is minus 110 Celsius. Over here, minus 120 Celsius. Now I'm asking you, what is the temperature at the top over here? Okay, please try. We have minus 90 over here. And then the next curve over here, this is minus 80 Celsius. Okay, if you have to estimate the top point over here, what is the temperature? Okay, please respond, any one of you.
Will it be minus 85 Celsius, sir?
Minus 85? Is it closer to minus 80 or is it closer to minus 90?
Close to minus 90.
Is that right? This point? Minus 90 is this. Minus 80 is this. Okay, our point is over here. Is it closer to minus 80 or closer to minus 90?
80, sir, 80.
Minus 80. Okay, okay. If it is closer to minus 80, let's assume this is minus 83. Okay, because it is closer to minus 80 here. This is minus 83, and then this is minus 90. That's the way to estimate visually. One of you will say 83 minus, the other one will say 83.5, the other one will say 82.8. So approximately it is minus 83 Celsius. That is the critical temperature of the methane. Now I'm asking you, what is the critical pressure of this methane? Okay, let's read to the left over here. Critical pressure. Okay, help me to estimate. The point is approximately here. What is the value of the pressure? Okay, please respond.
Is it anywhere to 7?
7? No. Why is it no? Because 1, 2, 3, 4. This is 2. This is 3, right? This is 4. This is 5. So it is in between 4 and 5. Is it right? This pressure, it is in between 4 and 5. If you answer 4.5, all right, that may be true. Okay? But it is not 7 though. This is 5, this is 6, this is 7, 8, 9, 10 over here. Okay? That's the way how to read the pressure from the Molar diagram. Okay? Any questions up to this point to determine critical temperature and critical pressure? Okay, easy. This is easy enough. Okay. Now I'm asking you, I have superheated vapor at minus 100 Celsius, but the position is over here. Okay, let me get the point. The position is over here. This is a superheated vapor. The temperature is minus 100 Celsius. Now I'm asking, what is the enthalpy of this point? Please respond.
Minus 300, sir.
Okay, let's read over here. Yeah, that's correct. Minus 300. What is the unit?
Kilojoule per kilogram.
Kilojoule per kilogram. Of kilogram what? Kilogram of methane. Because it is the curve of the methane. Okay. Our point is over here. Now I'm asking you, what is the pressure over here? Let's read to the left. Okay, the position is here. The pressure may be 1.3, something like that. Okay, let's read over here to the left. Because 2 is over here, 1 is over here is approximately maybe 1.3, 1.4. The unit of that pressure, it is megapascal. Okay, that's the way to read the enthalpy. Okay, up to this point, are there any questions on how to read the enthalpy? Easy, this is easy. Okay, now there is another way to read the entropy. Okay, if I have a point at 300 negative enthalpy kilojoule per kilogram, the pressure is 1 megapascal. The point is here. I'm asking, what is the entropy? What is the value of the entropy? How to do that? How to check that? Okay, the way is follow the curve over here. There is a curve bolded. This is the curve also in boldface, and we read the entropy here is 3.0. The entropy here is 2.0. In between, there are many curves. Let me make it bigger. If this is the entropy of 3.0, this is the entropy of 2.0, this is 2.2, this is 2.4, this is 2.6, this is 2.8, the entropy. Okay, I think the sign is negative entropy. And then what is the unit? The unit of the entropy is over here, kilojoule per kilogram Kelvin. Okay, this is how to read a Molar diagram. And then if I need to locate a certain point in between inside the dome, okay, let's try to check. I want you to check in a certain point here. Let me see over here. Okay, I have a point over here. It is in between the dome, inside the dome, between this point and between this point. Okay, I have the point is over here. The enthalpy is 700 negative. Okay, now I'm asking, is it more in liquid or more in vapor? This point, please answer.
Liquid, sir?
Liquid, yeah, because it is closer to the liquid. Over here it is 100% of liquid. In the 700, what is the percentage of the liquid? That is the question. Okay, how to calculate that? It is easy. I will measure the extreme point from this up to the right hand side. Measure the enthalpy. Okay, read the enthalpy downward here. The enthalpy is 350 negative. And then over here, the enthalpy is minus 750 approximately. So the delta, we know the delta. And then when we have a certain point here, we measure the delta of the enthalpy here. Minus 700 compared to minus 750. So this is 50 divided by the total, maybe is around 400. So the mass fraction is 50 divided by 400, things like that. This is the way to measure how much liquid and then how much vapor. If finally you find that the liquid is at this point, the liquid is 75%, then the 30% is the vapor. Is it percentage of moles or percentage of mass or percentage of volume? It is percentage of mass. Why? Because we have over here the enthalpy is per mass, per kilogram. So the ratio is the ratio of the mass ratio. Okay, up to this point, are there questions? I'm just showing how the logic first, how to understand the logic. Okay, clear? Now you are familiar with superheated, saturated, and then subcooled. We go to the problem of the test. Later you will be given the time for the test. There is a saturated steam table, there is a superheated steam table. Now you need to get familiar with the table. This is for water, this is not for methane. Okay, in the textbook, you can check from the contents of the appendix. It is steam tables, appendix E, the page is 680. So how to find out? Over here, you type 680 and then you enter, you get into appendix E of the steam tables. Okay, there is a description of the how to interpolate, how to estimate. Later we will come back to this point, but I need to show you the problem statement first. We have a saturated steam. We have the pressure at 43 bars. You need to find out the temperature and the quality. The quality means either the liquid fraction or the vapor fraction of the mass. This is, let me make it bigger. When we say XL, it is liquid mass fraction. When we say XV, it is vapor mass fraction. XL plus XV equal 1.0, or in percentage, it is 100%. So in cases that XL is 80% or 0.8, then XV is 0.2. Okay. Now let's try to understand the table. I think you have gone through this table, but I want to emphasize again the important point of this table. This is saturated steam, table E1. V is the specific volume. Why is it called specific? Because it is per unit of mass. Volume is cubic centimeter per gram. Therefore, it is called specific volume. We have specific enthalpy. It is called specific because it is per kilogram. Per kilogram of what? Kilogram of water. Is it vapor or is it liquid? Well, depending. If you are talking about the liquid, then it is the kilogram of liquid. If it is about vapor, it is kilogram of vapor. But if it is a mixture, then it is a per kilogram of the mixture. That is kilogram of liquid plus kilogram of the vapor. Okay. S is the entropy, specific entropy, kilojoule per kilogram Kelvin. U is the internal energy, specific internal energy, kilojoule per kilogram of water. Okay, now we have the group. This is the specific volume, this is the internal energy, this is the enthalpy, and then on the right hand side we have the entropy. Okay, now let's try one temperature, 256. What is the unit here? The unit is Celsius. What is in Kelvin? You just add with 273, you get 529 Kelvin. Okay, what is the pressure of that steam, saturated steam? This is the pressure, 4396.7. What is the unit? The unit is kilopascal. Okay, now remember, if I have a dome, on the left hand side it is the liquid, on the right hand side it is the vapor. Which dome we are talking about? If we have the P versus V volume, I think it is not here. Okay, it is somewhere in the textbook, but what we need to see is just the liquid is the one in the left hand side, the specific volume. The right hand side is the specific volume of the vapor. If I have 1.2 kilogram of liquid, and then I convert that, I put the energy, and it becomes into vapor all the way. What is the volume? The volume is 45, the same 1 kilogram of water. This is water vapor, this is water liquid. So 1.2 cubic centimeter, that is 1 kilogram of liquid, it will expand into 45 cubic centimeter of water vapor. Now, how to read the enthalpy? If I have liquid water on the left part of the dome, that is 100% of liquid, what is the enthalpy? The enthalpy is 1115. What is the entropy? The entropy, the enthalpy of the liquid, and this is the enthalpy of the vapor. Okay, what is the delta? The delta is, over here, 2798 compared with 1115. The delta is 1683. So if I want to vaporize 1 kilogram of water liquid into 1 kilogram of water vapor, we need to provide the energy is the delta, 2798 minus 1150. Okay, now we have another, that is the superheated steam. Remember, if we talk about the methane, superheated means on the right-hand side, outside the dome. Okay. In a certain pressure, if I have a pressure of 4,000 kilopascal over here, what is the temperature of the dome? Remember that minus 100 Celsius in the methane, in the water, if this is 4,000 kilopascal, let me make it bigger. If I have 4,000 kilopascal pressure, then the temperature, the horizontal line, is 250 Celsius. That's what we call saturated temperature. Therefore, it is written as T-sat. Okay, what is in Kelvin? You just add with 273 in order to get the Kelvin. But over here, it is written as Celsius. And then we have saturated liquid, we have saturated vapor, we have the property of specific volume, specific internal energy, specific enthalpy, and specific entropy. What is the unit of this? It has been indicated somewhere here, okay? Now, what does that mean? If I'm asking you what is the heat of vaporization of saturated liquid at 250 Celsius. Okay, let's imagine saturated liquid. It is in the left hand side. The temperature is 250 Celsius. The enthalpy in the left hand side is this. The enthalpy on the right hand side is this. And you are asked, what is the heat of vaporization? Okay, this is the difference. 2800 minus 1087. That is the heat of vaporization. The unit is kilojoule per kilogram. Okay, clear? Now this is about the saturated. But what happens, it is in the table of the superheated. Why do we need this part? Because later we need to check how far our temperature or pressure is from the saturated conditions. Now how to read this? There is a temperature in Celsius, there is a temperature in Kelvin. So if I have here 325, what is this? This is temperature in Celsius. What is in Kelvin? This is 598. This is in Kelvin. Okay. What is the enthalpy? If I have superheated steam at, okay, let me select over here. I have a superheated steam at 4,000 kilopascal and the temperature is 300 Celsius. What is the enthalpy? Well, this is the enthalpy, 3030.8 kilojoule per kilogram. Is it inside the dome or is it on the right hand side of the dome? Please respond. 300 Celsius. Is it inside the dome or on the right hand side of the dome, outside? This enthalpy, 3030.
Right hand side, sir.
Right hand side. It is right hand side and outside of the dome. Okay. Why is it not inside? Because the extreme right hand side of the dome is 2800. Okay. Remember, this is left hand side of the dome. This is right hand side of the dome. And then any values above 2800 enthalpy, it is outside the dome. Therefore, we have 2886. It is outside the dome because it is more than 2800. 2900, it is above this enthalpy. How about these dots over here? Well, these dots, it is area of the saturated vapor. So it is not filled. We just filled the superheated part. So the enthalpy is above 2800. Okay, this point. What is the pressure? This is the enthalpy. The enthalpy is 2886. What is the pressure? The pressure is 4,000 kilopascal. What is the temperature? The temperature is 250 Celsius. Okay, is it clear? Any questions to read the superheated vapor? Superheated vapor over here. Okay, clear? Now, if I have to determine the enthalpy at Celsius 260, how to do this? The value is over here in between 260 Celsius. The pressure is 4,000 kilopascal. What is the enthalpy here? Well, it is in between 2800 and 2900. Maybe it is 2950. Okay, to be exact, we have to do the interpolation extrapolation. In the textbook, on page Appendix E, that is page 680, there is the procedures for the interpolation. Okay, let me go through it quickly. Oops. This is an example. If I have the temperature 140 Celsius, the enthalpy is this, 2733 kilojoule per kilogram. And then 142 Celsius, the enthalpy is 2736. You are asked, if the temperature is 140.8, what is the enthalpy over here? Okay, now let's check. What is the delta of temperature here? The extreme 140, 142, the delta is 2 Celsius, right? What is the delta over here? 0.8. Okay, what is the delta over here? This is 1.2. 0.8, this is 1.2, the total is 2.0. Okay, now I am asking, the enthalpy over here, the value, is it closer to this H1 or is it closer to the H2? Please answer. The enthalpy in between. Is it closer to the H1 value or closer to the H2 value? This is 0.8, the delta. This is 1.2, the delta.
H1, sir.
H1, yeah. It has to be closer to H1. Okay, how to calculate that? This is the way to calculate. I have 1.2 divided by 2 Celsius. This is 1.2 Celsius. I have 0.8 Celsius divided by 2 Celsius. That is the extreme, the delta extreme. Multiply by this, I get the 2734. 2734 is closer to 2733 compared to 2735.6. Okay, so this is the answer, and this is how to estimate exactly or calculate exactly the values.